Behold the Lord of the night skies, the elixir of life, the moon. It is said that Lord Ram, as a baby, fascinated by the beauty of full moon in the night sky, wished to play with it. Not wanting to disappoint the child, Kaushalya brought the moon within reach of the young, innocent Ram. Unfazed and unchanged since time immemorial, a silent witness preserving the story of the universe, the moon has inspired children, poets, and scientists alike. And as it prevails today, India's Chandrayaan brings the moon within reach of scientists world over. India's first mission to the moon, Chandrayaan-1, was launched on October 22, 2008. PSLV C-11 injected Chandrayaan-1 into a highly elliptical transfer orbit ETO measuring 250 by 22,000 kilometers. In the series of planned maneuvers, the orbit was raised in steps. The first event was that of LAM firing near the perigee, shifting the spacecraft to Earth-bound orbit EBN-1 of 300 by 37,000 kilometers. On the fourth day, Chandrayaan-1 was moved into EBN-2 of 336 by 74,000 kilometers. The next day, the spacecraft's orbit was raised to EBN-3 of 348 by 1,65,016 kilometers. On the sixth day after launch, Chandrayaan-1 was shifted to EBN-4 of 460 by 2,66,612 kilometers. After staying in this orbit for nearly 6 days, on November 3, 2008, the spacecraft was pushed into EBN-5 of 977 by 3,79,454 kilometers. It was for the first time that ISRO was stepping out of the Earth's orbit to explore the space beyond. Navigating into deep space for about 5 more days, the spacecraft entered the lunar sphere of influence on November 8, 2008. When the spacecraft was about 500 kilometers above the lunar surface, a very critical lunar orbit insertion maneuver was carried to place Chandrayaan-1 in the lunar polar orbit. On the 22nd day, first of its 11 payloads, Moon Impact Probe (MIP) was commissioned. On November 14, 2008, MIP acquired first images of the surface of the Moon ever taken by any Indian mission. The 35 kg MIP, with the colors of the Indian flag painted on it, touched down on the lunar surface at 8:31 p.m. IST. It is known to have landed in the South Pole Aitken Basin of the Moon. The data collected by MIP is being analyzed by scientists at Vikram Sarabhai Space Center, VSSC, Thiruvananthapuram, and Space Applications Center, SAC, Ahmedabad.
A huge volume of data has been received. This data is archived in our data center at Bailalu near Bangalore, and from there it has been distributed to the scientists for their initial assessment. The initial assessment clearly shows that the performance of the instruments are highly satisfactory and the quality of data is extremely good, and we will be able to extract lot of information out of these details which is coming from the Chandrayaan.
Next to be activated were the two Indian Space Research Organisation ISRO payloads, the Terrain Mapping Camera TMC and the Hyperspectral Imager HiSci, both developed by Space Applications Centre, SAC, Ahmedabad.
Basic principles governing remote sensing of the Earth and the Moon are same. However, there are differences. On the Earth you have the atmosphere, whereas on the Moon you have no atmosphere. Also, there is no water as we see on the Earth on the lunar surface, and there is also no vegetation. So, the spectral variations that one sees on the lunar surface are very less compared to what you see on the Earth's surface. In addition, on the lunar surface we cannot have the ground truth in situ ground observations to verify what we see from the instruments, just like we do it on the Earth. However, we do overcome this problem by having a complementarity of instruments of various spectral regions, and also from the earlier missions that we have the data, we use it to make inferences of the Moon surface.
The reflected response of electromagnetic radiation from the lunar surface is collected by the remote sensing instruments and stored on the onboard solid-state recorders SSRs. The data is formatted and transmitted to ground when the satellite is in the Earth's visibility. The data from the SSRs is received at the ground stations of Indian Deep Space Network IDSN, ISRO and Applied Physics Laboratory APL, NASA. The data collected from APL is forwarded to IDSN located at Bailalu. The data from all the payloads is then sent to Indian Space Science Data Centre ISSDC Bailalu, which is the hub for science data pre-processing, dissemination and archival. Raw data from TMC, HiSci and other imaging payloads is scrutinized for the image quality and clarity. Quick Look Display QLD software enabling the instant viewing of this data during reception at ISSDC is employed. This data is pre-processed before it actually reaches the scientists for analysis. The software for processing the TMC and HiSci data, both at ISSDC Bailalu and SAC Ahmedabad, are developed by Data Products team at SAC Ahmedabad. This partially processed raw data is parallelly sent to the respective payload operation centers POCs, where it is again processed to generate different levels of products. At POC situated in SAC Ahmedabad, the TMC and HiSci parameters for geometric correction are computed and provided along with the product. The height information is derived using the TMC data and a digital elevation model DEM is prepared. The processed data of TMC and HiSci is now available to scientists for first-level analysis of the Moon. The terrain mapping camera TMC onboard Chandrayaan is designed to take 3D views of Moon surface so as to capture all the undulations and the ruggedness of the lunar surface. TMC at an altitude of 100 kilometers covers 20 kilometer swath at 5 meter resolution, which means that the area of 5 meters by 5 meters on Moon's surface will appear as 1 pixel in the imagery. The payload is a stereoscopic camera providing 3 views, fore, nadir and aft by 1 set of mirrors. The 3 views will enable the generation of 3D elevation model of the lunar surface.
These 3 views of this Moon surface data is collected and transmitted to ground via a recorder on board the Chandrayaan-1. Now, this camera design itself makes use of refractive lens assembly, which has been realized at our laboratory of electro-optics, LIOS, Bangalore, and a set of mirrors also fabricated at LIOS. The detector which is used in this camera is a special device called an active pixel sensor. This active pixel sensor makes use of 4000 element linear array, and each element is of 7 micron by 7 micron size, which on the moon surface translates to 5 meter by 5 meter. So, we say we get a swath of 20 kilometers on the moon with 5 meter resolution.
As we all know, the moon, just like Earth, is a world of mountains, conical hills, ridges, volcanic flows, plateaus, plains, lowlands, and of course, lots of craters. The lunar surface is broadly divided into highlands and mares or maria. The lighter regions seen on the surface are the highlands and are dominated by mountains, while the plain dark mares feature are nearly circular, low-lying basins. The near side of the moon, which always faces the Earth, is dominated by the dark mares, which early astronomers thought were seas. The far side of the moon, which is never seen from the Earth, has fewer maria and is more heavily cratered, a puzzle for all scientists to crack. The prime meridian region is boundary area between the near side and far side and is a mix of mares and highlands. Both polar regions are highland areas. The 3D TMC maps of the lunar topography are being interpreted at SAC Ahmedabad to identify different surface features on the moon. Image strips acquired on November 13th, 15th and 16th, 2008 from the near pole and equatorial regions were taken for the initial observation studies for TMC payload. It is a known fact that the moon shines by reflecting sunlight. Lower angle of sun's illumination enhances the subtle features of the lunar surface as seen in this TMC image from the poles till the equatorial region. The TMC maps have revealed the images of what the scientists term as faults. Cone-shaped small hills, sinuous rills, and an important landmark of moon, the Sea of Lava. The TMC images show that the lunar surface is marked by craters of varying shape, size, and age. Based on its formation, craters on moon are termed as impact craters. An impact crater is formed when a meteorite strikes the lunar surface, forming a bowl-shaped hollow surrounded by a wall of rock. The material that is thrown out of the crater hollow is termed as ejecta. A typical crater, as seen in this TMC image, has a central depression confined within the inner walls, a circular rim representing the highest part of its wall, and an outward sloping outer wall. Some craters have star-like features around it, and they are known as ray craters, caused by the displaced glassy material from the crater due to impact. Images of young craters and also some old craters have been prominently captured by TMC. The older craters show signs of obliteration and smoothening of their surfaces, while the younger craters have sharp and prominent features. The floor of the crater is clearly seen, along with various features like small secondary craters, the impacted inner walls, the subsidence of the inner wall material, and the domal structures in the complex craters. Craters are records of the history and evolution of the lunar surface. The Moon, during the early years of its life, went through a period of devastating bombardment by meteorites. Their impact punctured the crust and formed craters all over the surface. Later, the rate of bombardment slowed down. A time of intense volcanic activity followed as large, deep craters were filled up with lava. The lava, over a period of time, cooled down and later solidified to form the Maria. With a negligible atmosphere and low gravity, Moon's surface has changed very little ever since. Over a period of several months, TMC has not only provided excellent images of the lunar features, but also that of our native blue planet. Earlier, while Chandrayaan-1 was on its way to the Moon at a distance of 70,000 kilometers, TMC was switched on, taking its first pictures of Earth. The Earth, as seen by TMC on October 29, 2008, as it goes further away from it. Later, while in the lunar orbit, when the spacecraft was in the Earth's visibility, it was maneuvered to take pictures of the Earth with India in focus. TMC study will observe lunar features and classify them from the geological point of view. The highlands and the mares of the lunar surface are remarkably different not only geologically but also chemically. The minerals present on the lunar surface hold answers to the mystery of its formation and evolution. The mares, rich in dark basaltic rock types which absorb more light, have heavier elements like iron, magnesium and titanium, indicative of meteorite impacts and volcanic activities. The highlands, rich in brighter breccious rock